Alright, this video is going to serve as your review for your exam. So we're going to review all the topics in the chapter, which include function behavior. Some examples would be absolute extreme values, critical points, rise and fall patterns, inflection points, and concavity, and finding the summary behavior. So let's start with the absolute extrema. Let's say we have f of x equals x to the 2/3 on the interval -2, 3. Let's find the absolute maximum and the absolute minimum. Candidates for the absolute extrema are endpoints and critical points. So let's find the critical points by taking the first derivative. Our first derivative is 2/3 x to the -1/3. If we set this equal to 0, we get x equals 0 as our critical point. Although the derivative is not defined at x equals 0, this is what the graph of y equals x to the 2/3 looks like. It's still a critical point because it has a horizontal tangent line there. Although the derivative is not defined because we'd have 0 in the denominator, which means the graph is not differentiable at x equals 0. But that doesn't mean there's not a horizontal tangent line there. There is. Because the graph isn't smooth, it's not differentiable, but it still serves as a critical point. So our candidates for the absolute extremes are x equals -2, x equals 0, and x equals 3. You're listing your absolute extremes as x values, but you are referring to their y values to distinguish. So the only reason we took the first derivative was to find critical points. F of -2, you're evaluating the function. We're not evaluating the derivative. This is -2 to the 2/3, which is 4 to the 1/3 power. F of 0 is 0 to 2/3, which is 0. F of 3 is 3 to 2/3, which is 9 to the 1/3 power. So now we could determine what the absolute max and min are by looking at the y values, and we're going to list them as x values. So we have an absolute max at x equals 3 because the y values are larger than any other. We have an absolute min at x equals 0 because the y value is smallest there than any of the other candidates. If we took a look at this on our graph, this is what we'd have. Local max, local min, also an absolute min, local max, and absolute max. Alright, let's determine the intervals for which f is increasing and decreasing for the function f of x equals -x to the 3rd plus 12x plus 5. So we're going to take the first derivative and determine its sign to determine if the function is increasing or decreasing. Okay, so we have the first derivative is -3x squared plus 12. We're going to set this equal to 0 to find the critical points. Let's factor out a -3. Which gives you -3 times x squared minus 4. X squared minus 4 is also factorable. So we have critical points of x equals -2 and x equals +2. So there are two spots in which the graph can change direction. That doesn't mean they will change direction. This is the only candidate for which f can change direction. So let's create a rise and fall pattern by evaluating the factors of our derivative. Now -3 is a factor of our derivative, so make sure you include that. -3 is a negative factor. We have a factor of x plus 2 and a factor of x minus 2, and the product of all these signs will be our sign of f prime. let's plug in a number which satisfies this interval. That would give you a negative number there, a negative number there. A negative times a negative is a positive, times a negative is a negative. The function is decreasing for this interval. Let's plug in 0. We already said negative 3 would be negative. 0 plus 2 is positive. 0 minus 2 is negative. Well, negative times a negative is a positive, times a positive is a positive. Since the first derivative is positive, the function is increasing there. Let's plug in a number greater than 2. We already said that negative 3 is a negative factor. Plug in 3, positive and positive. Well, a positive times a negative is a negative, which means the function is decreasing there. So f is increasing on the interval negative 2 to 2. I'm not including negative 2 or positive 2 because it's not increasing or decreasing there. F is decreasing on the interval negative infinity to negative 2 and union 2 to infinity. So let's use the second derivative as a shortcut to determine max or min. Let's identify the critical points of y equals x to the fourth minus 4x to the third plus 10 as a max, a min, or neither. So let's find the critical points. Y prime equals 4x to the third minus 12x squared. We'll set this equal to 0 to find the critical points. So let's factor out a 4x squared, leaving you with x minus 3 equals 0. So we have critical points of x equals 0 and x equals 3. Let's determine if these are this is a maximum or a minimum or neither, and let's determine if that's a maximum or a minimum or neither. Well, y double prime is the derivative of y prime, 12x squared minus 24x. And what we'll do is evaluate 0 and evaluate 3 and use their signs to determine if it's a maximum or a minimum. So instead of y double prime, I'll say f double prime of 0 is 0. That's funny. What does that mean? That means the second derivative is 0, which means that 0 is neither a max or a min. It's an inflection point. F double prime of 3 is, let's plug in 3 to our second derivative. That's 12 times 9 minus 24 times 3, which is 90 plus 18 is 108. 60 plus 12 minus 72, which is a positive number. So since f double prime of 3 is positive, that means it's concave up, because positive people smile. The second derivative determines concavity. Since this is concave up, that makes x equals 3 a local minimum. Alright, curve sketching. Creating a summary behavior. Let's create a summary behavior for f of x equals 1 minus 9x minus 6x squared minus x to the third. We're going to create a summary behavior for this. F prime of x equals negative 9 minus 12x minus 3x squared. Let's find the critical points by setting this function equal to 0. negative 3x squared minus 12x minus 9 equals 0. We have a GCF of negative 3x squared plus 4x plus 3 equals 0. Negative 3 times x plus 3 times x plus 1. So we have critical points of x equals negative 3 and x equals negative 1. Let's create a rise and fall pattern for this function. Well, negative 3 comes for negative 1. And we're going to use the factors of our derivative. Again, we have a negative factor here. We have factors of x plus 3, x plus 1. Multiply all these signs together for our sign of f prime. Negative 3 is always a negative factor. Plug in negative 4. And this would yield a negative sign there. Let's plug in negative 2 here. Positive, negative. Multiply these together, you get a positive number. Let's plug in 0. Positive, positive, giving you a negative sign of the first derivative. So my rise and fall pattern is as follows. Now we're going to create a concavity chart and combine all of that information. F double prime of x equals negative 12 minus 6x squared. Let's set this equal to 0 to determine any possible inflection points. So we have a GCF of negative 6, leaving you with 2 plus x squared equals 0. So set these both equal to 0. X squared plus 2 equals 0. X squared equals negative 2. You cannot take the square root of a negative number, which means what? There are no inflection points. Concavity will not change for this graph. Oh, I messed up. Second derivative's minus 6x. But that's a good example. If we got no values which satisfy f double prime of x equals 0, it means there's no change in concavity, which means it's always concave up or always concave down. So plug in a number to your second derivative, and its sign will tell you whether it's always concave up or always concave down. But just give me 1 second to erase all this. Sorry about that. The first derivative was this. Take the second derivative, and we get that. So pretty rookie mistake there. Sorry. Set this equal to 0. We get negative 6x equals 12. X equals negative 2 is our possible inflection point. So we're going to create a concavity chart which is broken up by that value. And we're going to plug it into the factors of our derivative. The factors of our derivative was just one of them, negative 12 minus 6x. Plug in negative 3, gives you positive 18. That's a positive number, concave up. Plug in 0, just because it's an easy number to work with. Whoops, negative means concave down. So now what we're going to do is combine this information onto one chart. So we're going to list all of our critical points and inflection points in ascending order. So we have negative 3, negative 2, and negative 1 were all of our critical points and inflection points. Decreasing until you get to negative 3. Decreasing. Increasing until you get to negative 1. All the way until we get to negative 1. Increasing, increasing. Decreasing after negative 1. Alright, concave up until you get to negative 2. Concave up, concave up. Concave down after negative 2. Concave down, concave down. So the concavity is telling you how to bend these lines. So bend it, creating something that should be bending upwards. So bend the middle of the graph down. which generates something that looks like that. Bend the line, creating something that's supposed to be bent up, increasing, but bellying downwards. So it's going to create something that looks like that. Bend this up, creating something that looks like this. And bend this up, creating something that looks like that. And then what we can do is connect all of our information, take these pieces and put them all together and say the general shape of the graph looks like that.